Hey everybody, Morgan here. We're on page 4 of our thermochemistry outline for Honors Chem. And we're going to be talking about phase changes today. All right? Now, when we have a substance like water, okay, and we know of it existing in 3 different phases, solid, you call it ice, liquid, you call it water, and water vapor, which you mistakenly call steam. Steam is actually liquid water that is condensed in the air, okay? So what's the difference between the water that's in these 3 substances? Well, it's all water. It's all molecular formula H2O, okay? It's just that the speed at which the molecules are moving and the distances between the molecules water molecules in the gas phase are very far apart from each other, flying around randomly, chaotically, quickly, bouncing off all the walls of the container. Okay? Now water in the liquid form, they're much, much closer together. They're still moving decently, okay, randomly, but they stay in the bottom of their container. Okay? So now if you heat a substance, what's happening? Well, based upon this idea, I think you figured out. The molecules move faster. The molecules are moving faster as the temperature goes up and up and up. Okay? So, let's talk about the phase changes that happen when we heat something. We start with a solid, then we go liquid, and then gas. When a solid turns into a liquid, that is called melting. When a liquid turns into a gas, that is boiling. Please do not say evaporation. Evaporation has a very specific definition, which we'll get back to. Gas turning into a liquid is called condensation, which is used as both a noun and a verb in the English language. And then a liquid turning into a solid is called freezing, one of the most misused words in the English language. You use it to indicate cold when it indicates a phase change. Now, a solid can go all the way to a gas. We call that sublimation. And a gas can go all the way back into a solid. We call that deposition. And you can actually observe water undergo all 6 of these phase changes, even in Southern California. It's possible. Okay? Now, the little lab that you did where you were heating up a beaker full of ice to generate a heating curve that looks something like this. Okay? When you take any solid and you plot time on the x-axis and temperature on the y-axis, okay, it's going to give you something that looks like this. The solid will heat up until it reaches the temperature that is called its melting point, at which point the temperature will remain constant. You have this plateau, this horizontal line here, okay, while the solid and liquid are in equilibrium with each other. It's melting. After it has all melted, the temperature can start to rise again, but it can only go up to its boiling point, at which point it's going to boil. Now, after the boiling point, after all the liquid is boiled, the temperature of the gas can be increased also. But while you are undergoing a phase change at these 2 places, temperatures remain constant. Now, for water, the melting point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. And that is assuming that everything is happening at 1 atmosphere applied pressure. We call that a normal melting point and a normal boiling point. Now, if we do this for another substance, it's still going to look just like this for any pure substance. It's just that these numbers are going to change. And the numbers here, the distance that we see, the run, the x-axis, that's different depending upon how much ice is there, how high the temperature you're heating it with is, what the substance is, etc., etc., etc. Okay, but it will always take this same basic shape. All right, thanks for tuning in. That was page 3 of the outline.